Here we'll see this problem based on the principle of superposition. I can see a diagram here which is a brass bar having cross-sectional area of 1000 mm square is subjected to axial forces. As you can see here, there is some axial forces, and we have to find the total elongation given the Young's modulus for this material is 1.05 into 10 power 5 Newton per mm square. So now first what we should do is we have to consider the individual sections here. So let's take this is section A, this is section B, and this is section C. So here I have separately drawn the sections A, B and C. Now if you see the forces here, section A is experiencing a 50 kilonewton outward force, which means here I have 50 kilonewton, and as a result even the other end of section A also will experience 50 kilonewton. So here I'll have 50 kilonewton. So if I have a 50 kilonewton force towards the right, then there will be a 50 kilonewton force towards the left also, and this is a reaction actually. So this means that totally I am getting 70 here. So the section B will experience 70 kilonewton force towards the left. So even this end also should experience 70 kilonewton, but I just have 30 kilonewton here, which means I have to add another 40 kilonewton. So adding this I'll get 70 kilonewton. So if I add 40 kilonewton, I have to take another 40 kilonewton in the opposite direction, which means here for section C I'll have 40 kilonewton towards the left, and towards the right already we have 40 kilonewton. So these are the forces acting for the individual sections. Now we have to find the elongation. Elongation for this we have to apply the Hooke's law, that is stress is equal to Young's modulus into the strain. The stress can be written as the force by area, so P by A, that is equal to E into elongation, that is del L by L. So we have to find the elongation, which means we have to find del L. So del L will be equal to P L by AE. So now we have to find all these four things, P, L and AE. So P, if we take the sections separately, so for section A we have we'll consider this P1. So P1 is 50 kilonewton, and L1 is 2 meter, that is L1 will be equal to 2000 mm. Similarly I can write P2 and P3. P2 will be 70 kilonewton and L2 is equal to, for this it is 3000 mm. Then P3 is equal to 40 kilonewton, L3 is equal to 1000 mm. So now and then the value of A. So this is have a uniform cross sectional area of 1000 mm square. So A is common for all the three sections, and also the Young's modulus is also common for all the three sections, since it is it has 1.05 into 10 power 5 Newton per mm square. So now applying all this for the separate sections. Let's do it for section A. For section A, you can see that del L will be equal to here P1 L1 by AE, that is equal to, what is P1 here, that is 50 kilonewton. So 50 into 1000, because we are converting this to Newton, so we have to multiply with 1000 here, into what is L1. L1 is 2000 here, divided by A, that is 1000, into 1.05 into 10 power 5. Similarly I can write for this is, let me take this del L1, del L2, del L2 will be equal to P2 L2 by AE. So here we found for section elongation for section B, and the values that we are getting are, for section A, the elongation is 0.9523 mm. For this I am getting, for section B I am getting 2 mm elongation, and for section C I am getting 1.4286 mm elongation. So the total elongation, that is del L, will be the sum of all the three elongations. Sorry, this value is not this. This is 0.3809. Now adding all these three, I am getting 3.33 mm elongation. So now since this is I am getting plus here, this is positive value, which means I have tensile load here. Overall, if you see, I am getting a tensile load. The whole bar is experiencing a tensile load. Now we'll see another problem in the concept of principle of superposition. So I have taken three sections here with different loads. Let's draw this section separately. This is section A, this is section B, and this is section C. Now the section A, you can see that it is experiencing 30 kilonewton outward force here. So the other end of this section A also will experience 30 kilonewton outward force, which is shown here separately in the free body diagram. Now the section B, if you see, we have the 60 kilonewton, out of which 30 kilonewton is used as a force for section A. Still we have 30 remaining. So in that 20 will be used for the section B. So the section B is experiencing 20 kilonewton, since the other end also is experiencing 20 kilonewton. But the difference here is this is going to be a compressive load, whereas for section A it was a tensile load. So still out of the 60 kilonewton, 10 kilonewton is remaining here. So this 10 kilonewton will be serving as a force for the section C. So it will have a 10 kilonewton rightward force, and even from the other end also we have 10 kilonewton force. So this will totally balance the forces here. Now applying this in the equation, del L equation, the elongation. So here you can see taking the forces separately for different sections. So this will give P1 L1 by AE. This will give the elongation for the first section, for the section A, P2 L2 by AE. You can see that I have written minus here, since the force here is a compressive force, whereas in the first case it is positive, since that is a tensile force. Similarly, for the third section also it will be minus, since even that is also a compressive force. So now overall, if you see, after doing the algebraic sum for this whole equation, if I get it positive, if I get plus del L, then the total force is a tensile force, and in that case I'll see elongation. Whereas if I get minus del L, which means the algebraic sum I got there is negative, in that case the overall force will be a compressive force, and in that case I'll see reduction in length. So this depends on the algebraic sum of this equation. Now carry on this topic. Now here we'll see that if I apply a load P, and this load is actually acting for every section is experiencing the same load. So in that case, I cannot say this is the principle of superposition concept, because in the principle of superposition we have different loads, whereas here we have a single load. So still the equation, the basic concept is same here. Del L will be equal to PL by AE even in this case, but all the sections have different area here, A1, A2, A3, and even the length is also different for all the sections. L1, this is L2, and this is L3. So in that case, the equation I can write del L will be equal to, since the force is a constant here, so the force will be outside, and even the Young's modulus for this material is constant, so that is out. So I'll have L1 by A1 plus L2 by A2 plus L3 by A3. Now consider that if this bar is made up of different materials, so all this section is made of different materials, so the Young's modulus for all these sections will be different. Say this is E1, this is E2, and this is E3. So in that case, the equation will be P into L1 by A1 E1 plus plus E1 plus L2 by A2 E2 plus L3 by A3 E3. Similarly, even here also, for the simplicity in calculation, I can write del L will be equal to, since A and E is constant, so I can take AE outside. So I can just take P1 L1 minus P2 L2 minus P3 L3.